Thanks for joining me today for this session, which is about decoupling serverless workloads with Amazon EventBridge. My name is James Bezic, and I'm a developer advocate here at AWS Serverless. I've been a DA for quite a long time, and I've built some fairly large applications using only serverless technology. Before I was a DA, I was a product manager for quite a few years, and also a software developer for a long time as well. The most important thing on this slide is take a note of my Twitter handle and email address. So if you have any questions about serverless at all, please feel free to reach out to me anytime, and I'll do my very best to help. We have 30 minutes today, and this is a 400 level session, so I'm going to cover three areas. First, I'm going to review the existing challenges with microservices and how EventBridge helps to solve these. I'll cover integration patterns with EventBridge, and I'll also show how to extend the capabilities of the cloud with SaaS partners. I'll talk about controlling access to resources and how security works with EventBridge. And finally, I'll show you how to decouple architectures using events and with the serverless application model, also known as SAM. Throughout the slides, you'll see links to code and GitHub repos, so please follow those to learn more about the concepts that have been covered. So let's take a quick look and a quick review of some of the challenges of microservices. When you first start building microservices, you have simple architectures like this. Here are two services, an order service and an invoice service. In the initial stage, these are decoupled and everything is very simple. But what happens when we start to add more services that integrate with the order service? Well, the order service starts to have more responsibilities and more complexity. And each of the integration services must understand how to provide retry semantics. And maybe the order service has to bundle an SDK for each. And even if each downstream service publishes its own API, the order service is on the hook to talk to each one of those. So any backwards incompatible changes to the APIs, and then the order service team is also on the hook to update their system. And so in the long term, there are more and more services out there that need data from the order service. And in this model, those teams are blocked by the order service team to implement the changes that they want. And so they cannot operate independently as they once could. And it creates unnecessary friction in the process due to the integration cost of hooking these services together. And this slows down our development process. Here's the same e-commerce application with a couple of additional downstream services that I've added, fulfillment and shipping. In the happy path, everything works as expected. The order service triggers the invoice, payment systems, and updates forecasting as well. And then once the payment clears, this triggers the fulfillment and packing of the order. And then once that's done, we then inform the shipping service to request tracking information. But what if the fulfillment center cannot find the product because they're out of stock? Well, the fulfillment system may have to then alert the invoice service, and then perhaps they have to reverse a payment or issue a refund or a partial credit. And then the shipping service may have already been triggered, so you might have to send another message to handle that. And any of the forecasting information may have to be adjusted too, so you have to send that message too. And this is just one potential problem in one service that you may have, just one remediation workflow. So the microservices model can end up being very monolithic and fragile when you're trying to deal with these error states. Now those are some of the challenges, but there are also many benefits to using microservices if you get this right. In a well-designed microservices architecture, you can maintain loose coupling between the services. Microservice-based systems can be significantly more scalable, and indeed that's why many AWS services are microservices-based, precisely because of this. You can build systems that are much more extensible because of new features and applications that can consume events without impacting existing systems. And much of the complexity of large systems can be easier to manage in the microservices model. And of course, you can design for high levels of availability with many patterns available to help you develop resiliency and fault tolerance. So Amazon EventBridge is a serverless event bus service, and it makes events first-class citizens across your workloads. It helps you ingest and route events from SaaS applications, AWS services, and your own systems. It's not a completely brand new service. It evolved from CloudWatch events, so it's already processing trillions of events every month. A couple of the most important features in an event bus are that it provides an endpoint where an event producer can send events. The router manages directing and filtering those events to the appropriate downstream consumers. And consumers can get the events that they care about reliably, while the producers remain completely decoupled. From the previous example with the order and invoice service, introducing an event bus is simple. The architecture looks like this. The order service sends events to the bus, which is configured with rules that determine which downstream systems get the event. Some targets only care about certain events, whereas others want all the events. Either way, the router now takes on the complexity of ensuring that these events get propagated appropriately to each downstream service. So let's take a look at some integration patterns that you can build with EventBridge for your serverless applications. EventBridge accepts events from event sources, and these can be any one of 95 AWS services, or your own Lambda functions or applications, or SaaS application providers like Auth0, Datadog, or PagerDuty. There are three types of event bus. There's a default bus, which is always available in every account, and that's where AWS events are routed to. There are custom event buses, which you can create for your own applications, and there are SaaS event buses, which are created when you configure SaaS applications. There are many potential targets too, including Lambda, Kinesis, step functions, API gateway, EC2 instances, SNS topics, SQS queues, and you can also route events to buses in other AWS accounts. This flexible and non-prescriptive design allows you to create a wide variety of integration patterns. The first example is a scalable webhook. A webhook is an HTTP endpoint that's callable from another service, which could be something like a microservice or a third-party application. Webhooks are really common, but they actually do have some problems. So webhooks are often public endpoints that can receive sudden bursts of traffic. And if the backing application cannot scale to meet that traffic, it can experience an outage when those traffic surges occur. So in this case, the caller of your webhook may not have retry or error handling logic, and you can lose messages. EventBridge provides a very simple solution here. In this architecture, the HTTP endpoint routes directly to the event bus using a service integration. The HTTP API service integration passes events directly to the EventBridge service. The bus then passes these messages to an SQS queue for durable persistence. In this example, a Lambda function then processes those events, but really you could use any service you choose to process those events. Now, there are a couple of benefits of doing this. One is you can change the destination of the webhook easily by adding new targets to the rule, and you can control the rate of consuming the events in the Lambda function by managing the concurrency controls. So how is this configured in an AWS SAM template? Well, an HTTP API configuration uses this open API specification shown here on the left. This defines EventBridge as the target and specifies the credentials that will be used. It also specifies how the request parameters in the API call are mapped to the JSON body of the event. In this example, I've mapped the detail type and source attributes for the event bus. On the right is an EventBridge rule that's configured to filter for a source of my webhook to match events from this HTTP API endpoint. It then defines the SQS queue as a target. You can download and deploy this example from that GitHub repo shown on the screen. The second integration pattern that's interesting can help you respond to workflows. In the opening example, I showed an e-commerce application with these 6 different microservices. Some of these services, like payments, have their own complex logic internally. If you think about payments, payments have different types. It could be cash, credit, or check, for example. They can succeed or fail in terms of processing. They can also be reversed, or they can be reversed partially, and they can take a long time to complete. So sometimes they can take days or even weeks to complete, especially in the case of things like checks. The payment service would be a great candidate for step functions, given the complexity of this particular workflow. A workflow that emits events for all the different statuses is useful for extensibility and allowing other services to respond to changes. Integrating step functions with EventBridge allows you to do exactly that. As state machines begin and end, or steps progress, it can emit events back to the bus. Now, there's no cost for doing this since the events are sourced from another AWS service. Now, if nobody's listening to the event today, that's fine, but it gives you the capability tomorrow of allowing other teams to build their applications on those events. This GitHub repo shows you how you could deploy a step functions workflow, emitting events to EventBridge, and then creating rules for a Lambda function. The events emitted from the workflow look like this. The detail type shows a status change. It provides relevant ARNs, timestamps, inputs, and other data. So to consume an event that's interesting to your app, you simply build a matching rule. Unlike the invoice example I showed earlier, this allows integrations without needing any type of code changes in your software. It also allows other teams to build their own services on top of your workflows. And as the event producer, you're enabling that capability by creating the event, but you're not responsible then for the application that other people build. This third example uses CloudTrail to source events. Many AWS services and actions can emit events to EventBridge. This includes services like AWS Batch, Code Build, AWS Glue, IoT Greengrass, and many more. It also includes actions like sign-in events from the console or tag changes on AWS resources. You can use these to build serverless workflows to take action when a user logs into the console, for example, or take action when tags change on resources. Beyond these supported events, you use EventBridge with services that do not emit events by using AWS CloudTrail. EventBridge can listen to any events that are logged through CloudTrail. All events that are delivered via CloudTrail have a detail type attribute of AWS API call via CloudTrail. And this opens up a variety of very useful integration patterns. One example is allowing multiple S3 buckets as an event source for a Lambda function. When you use the default integration between S3 and Lambda, you cannot have overlapping subscriptions. If one bucket is publishing all the events to one Lambda function, you cannot then create a second Lambda function with the same subscription for the same bucket. However, if you enable CloudTrail logging for your S3 buckets and consume this event source in EventBridge, you can have overlapping subscriptions. And this means you can have events from several buckets triggering one or more Lambda functions. Or you could have the same prefix or the same suffix patterns trigger multiple Lambda functions. After enabling CloudTrail, you then create an EventBridge rule to define which bucket events should trigger which function. In this example, the event pattern filters for put object events on 3 named buckets. You can modify the behavior of when the Lambda function is triggered simply by modifying the EventBridge rule. You can take this a step further by using content filtering syntax in EventBridge rules. Imagine, for example, you need to invoke a Lambda function when an invoice is saved in a monthly sales bucket. These buckets follow the naming convention sales, then the month. To do this in the EventBridge rule, you can simply prefix the rule using an operator to match any bucket beginning with mysales dash. The native S3 to Lambda event source mapping only allows you to map functions to existing buckets. This approach allows you to dynamically map events, even for buckets that haven't been created yet. So when new buckets are created, such as mysales April or mysales May, matching events from those buckets will then trigger the function. CloudTrail logs additional information about S3 events, such as object size, principal, source IP address, and many attributes. You can filter on any of these complex rules to match specific sets of events. Then your rules can trigger Lambda functions, step functions workflows, or any other targets that you need. Take a look in the code repo to see how this works in detail. This pattern can allow you to decouple event sources from event consumers, can really make it easier when you're working with existing buckets or looking to decouple larger applications. Many of our customers use software as a service services as essential parts of their IT infrastructure. One of the most interesting features of EventBridge is the ability to integrate with these software as a service solutions. And this enables a wide variety of patterns in robotic process automation, or RPA, and workflow automation. There are currently about 30 partner integrations available from services like Auth0, Epsagon, Freshworks, PagerDuty, Symantec, and Thundra. If you're developing software as a service solutions, you can also apply to become an integrated partner. It's a fairly simple process. This integration replaces the typical polling and webhooks integrations that are commonly used to retrieve data from APIs. Polling is compute intensive and can be a difficult approach in terms of fetching data updates. It's not real time and it doesn't work well for larger payloads. Webhooks also can be difficult to scale, and often they only have static API key-based security, and they create a publicly callable endpoint that you have to secure. This integration replaces both of those methods. Instead of having events from partner event sources appear directly, they appear in your partner event bus in your AWS account. And this allows you to treat this data in the same way that you treat other event data from AWS services or your own applications. You can apply rules and targets to these events to complete further processing as well. So this solution is much more secure, since the data that you're passing from the provider event bus to your own event bus is happening without using API keys over the internet. It's also fully managed and scaled automatically. And once you've configured the integration, there's nothing that you need to do to maintain it or manage it. So this provides a robust, near real-time and simple way to bring events from your SaaS providers directly into your applications. Here are three really useful integrations that I want to highlight. These show the coding patterns that you can take that are needed to integrate with any of these partners. If you use Shopify, you can consume inventory, ordering, and payment events, for example. For Zendesk customers, you can receive events, maybe run sentiment analysis on tickets, and update urgency levels as needed. And with BuildKite, you can integrate with events emitted from CI/CD processes. When you combine the capabilities of these SaaS providers and with AWS services and your custom code in Lambda functions, it really provides virtually limitless extensibility for your applications. Controlling access to EventBridge resources is an important part of the security of event-driven applications. EventBridge provides very granular security controls integrated with IAM to give you precise authorization and access controls over event buses, rules, events, and targets. Identity and Access Management, or IAM, is a foundational service in AWS and fundamental to providing security for serverless applications. You can implement identity-based policies using IAM with familiar policy elements such as resource, action, effect, and role. You've probably used these with other services. You can attach permissions to users or groups or to roles. There are also AWS managed policies available that bundle multiple actions together to make it easier to build your own policies. For example, there are policies and roles that provide full access, read-only access, or invocation-only access. For EventBridge to send events to a target, it needs an IAM role, and the list of EventBridge actions, API actions, shown on the right here, can be used to explicitly define those permissions. When a rule is triggered in EventBridge, all of the targets of the rule are invoked. To make API calls against your resources, EventBridge needs appropriate permissions. For Lambda, SQS, and SNS, and CloudWatch Logs resources, EventBridge relies on resource-based policies. These are attached to a resource instead of an IAM identity. As a result, the principal in a resource-based policy may be an AWS account, or it could be an AWS service. Here are a couple of examples. The policy on the left grants access to EventBridge to publish messages to an SNS topic. The condition statement restricts permission to only a single defined rule using the source ARN. This means the same policy cannot be used by another rule, or it cannot be used to publish to a different SNS topic. You can also apply resource policies to the schema registry as shown on the right. The policy is attached to the registry itself, and to provide access, you have to specify the schema ARN and the registry ARN in the policy. Here, the principal is a single specified AWS account. You can also use an array of accounts or an organizational ID instead. Tags can be a really powerful way to group AWS resources by application or project name, or environment. You could set an environment such as production or testing. EventBridge supports policies that use tags. This example here shows how you could restrict access to resources that include a tag with the key environment and the value production. This allows you to provide specific levels of access based upon tag values, and these can be more restrictive than other policies in place. You can control who can access events and what actions they can take. You can use policies to separate who and what can create a rule and consume an event, and who and what can invoke a target. To create a role must have an events put rule action, but this by itself doesn't allow you to invoke a target. To do that, you must also have a role that has the events put targets action. Here are some more examples of how to use individual actions to implement fine-grained access control. Understanding how to use condition keys in your policies is really important here. You can restrict the type of events a user can consume by using condition keys. Source and detail type could be specified in the policy, or restrict which policies and resources can be added to a rule. In other words, limit the targets on a rule. And for this, you use the target ARN condition key. You could also restrict the events originating from CloudTrail by using the detail.useridentity.principal_ID condition key. This deep integration that EventBridge has with IAM provides you with the powerful access control capabilities over the resources that you have. You can decouple larger applications by using EventBridge with the AWS Application Services model, also known as SAM. SAM can help you build and deploy serverless applications using YAML templates that transpile to CloudFormation. It's an infrastructure as code tool, so you can create repeatable, versionable deployments of infrastructure. There are several benefits when using SAM with EventBridge. First, you can build smaller microservices that communicate using events and you deploy with SAM. This can really help you with simplicity in your workload. If your organization has teams of developers working on separate services, it allows each team to be in control of their own service and operate independently. SAM can make it safer and faster to deploy new versions and features of your software. And since many developer teams now develop more features and softwares more often, building microservices that emit events can help with extensibility, allowing other teams to consume events to develop their own applications. And when you build these decoupled microservice-based applications that communicate with events, it can be easier then to understand the interactions of services and see what each service is doing compared with monolithic alternatives. I wrote an example application to illustrate some of these benefits, and there's a blog post explaining it at the URL shown on the screen. In this first example, I created a document indexing application. There are multiple Lambda functions here that listen for new objects arriving with different file types. These functions read those files and then use machine learning services to detect the content before indexing it in the Amazon Elasticsearch service. This entire app is a mono repo. All of the Lambda functions and AWS services are defined within a single template. Even at this size, this application is less extensible and flexible than I would like. The process of parsing and converting content is fairly brittle and tightly coupled, and it would be hard to share ownership with many developers to build more features. So in this second example that I built, I decoupled this application using EventBridge. The URL shown on the screen at the bottom is the second blog post that discusses the process involved and provides a link to the code repo of the entire application. After these changes, the document indexer application can now dynamically listen to a range of S3 buckets by listening to CloudTrail events. Each file type converter becomes a generic type of function, consuming an event from EventBridge. This makes it easy for developers to create new converters for different file types without impacting the existing application. And while the loader function still integrates with Elasticsearch, by adding or changing a target on an EventBridge rule, I could send all of the indexing data to any other database or service that I choose. So by converting the application to become event-centric, I simplify the logic flows and make it easier to understand. And by splitting up the application into separate SAM deploying microservices, I make it easier and faster to deploy, and also make it easier for other teams to extend functionality. As you build decoupled applications that communicate with events, one challenge that emerges is keeping track of the format or schema of those events. As new versions of services are released, developers sometimes change event formats and add other attributes. So one feature of EventBridge that helps here is to keep track of events is the schema registry. This was created to allow you to discover, create and manage open API schemas for events that are flowing through your event buses on EventBridge. You can find schemas for existing AWS services, and you can create and upload custom schemas or generate a schema based upon events on the event bus. Once turned on, schema discovery is automatic, and then the AWS toolkit supports both VS Code and JetBrains. For all schema types in EventBridge, you can generate and download code bindings to quickly help you build classes based upon those events. This can really help you accelerate development and reduce manual errors. In this screenshot, you can see an example schema for a user event. The schema registry identifies separate versions of the event schema, and then the Download Code Bindings button lets you download the bindings, and you can also do this directly from the AWS toolkit in the IDE. After downloading the bindings, this automatically generates classes based on the event. And this works for type-safe languages such as Java, Python, or TypeScript as shown here. You can then immediately use these classes in your applications, letting you focus on writing the business logic and not the boilerplate. So to quickly recap what I've shown today, EventBridge can help you decouple your microservices, especially as they start to grow. The event bus separates event producers and consumers, helping to pass and route messages. It helps with scalability, scaling up and down traffic automatically, and this can be used with other services like the scalable webhook, a pattern you can use for providing resilience behind an HTTP endpoint. Extensibility is an important benefit. You can consume events from a growing list of SaaS partners, and you can emit events from your own applications and step functions workflows. This allows other development teams to help to build new applications and for your team to create new features in the future without impacting existing code. I talked about the security features of EventBridge and showed the deep integration with IAM to provide granular control over event buses, rules, and targets. And then I showed how you can use SAM to accelerate development and automate deployment. When combined with EventBridge, you can use SAM to break apart larger applications into smaller decoupled services that communicate using events. Thank you very much for your time today. My name is James Bezic. I'm a developer advocate for the AWS Serverless team. Please don't hesitate to reach out to me and contact me if you have any questions at all about building serverless applications.